In this video, we are continuing the Achieve 4.3 homework assignment starting at number 13. And all of the problems 13 through 22 continue with the first derivative test, where we're trying to determine when a function is increasing, decreasing, and when it has maximum and minimum values. So in number 13, you see that we have a fourth degree function, which we know has an infinite domain. So the domain is going to be negative infinity to infinity. We need to find the places where the derivative is equal to 0. So derivative is easy. We just use the power rule on each one of the individual terms. Now, after doing that, I was thinking, especially since I saw that the second term has a coefficient that's 3 times the first term, and then that same pattern existed between the third and fourth term. So I knew that this should be able to be factored by grouping pretty nicely. So I grouped the first two together and I pulled out a common factor of negative 7x squared. When I did that, I was left with x plus 3. Then in the second two terms, I did the same thing. I factored by greatest common factor, take out the 28, and again, you're left with x plus 3. Now, using the factoring by grouping technique, I can say, well, between this term and this term, they both have the common factor of x plus 3 multiplied by what's left over, which is just going to be the factor of negative 7x squared plus 28. Now, I could factor or further factor that second term, but I don't need to. I can go ahead and set it equal to 0 now. When the first factor equals 0, I get x equals negative 3. If I set the second factor equal to 0, I'll get 28 is equal to a positive 7x squared. And then divide by 7 on each side, x squared would equal 4. Take the square root of both sides, and you get x is equal to positive and negative root of 2. Now, I have all three of my critical points here. And that makes sense that I have 3 critical points, because I would have expected 3 turning points of a fourth degree function. I have them. Now, I'll go ahead and break up the domain of this fourth degree function. I'll say, well, it starts at negative infinity. The first test interval is going to go to your smallest critical point, negative 3. Then you're going to go from that critical point, negative 3, to the next one, negative 2. Then you'll go from negative 2 to the largest one, positive 2. Then you'll go from positive 2 to infinity. So 3 critical points are going to create 4 test intervals. I choose test points that fit within each of these intervals. And then I think about what these test points are going to do into my factored first derivative. So whenever I plug a negative 5 into this factored first derivative into the first term, I can see that negative 5 plus 3 would be negative. Into the second term, I would have negative 7 times 25 plus 20. That's going to be a negative. We know the product of 2 negative numbers is a positive. Thus, I know my function is increasing from negative infinity to negative 3. Now, what about my next region? I said, well, between negative 3 and negative 2, I'm letting negative 2.5 represent that area. So when I plug the negative 2.5 into your first factor here, negative 2.5 plus 3, that's going to be a positive. When I plug a negative 2.5 into my second factor, it would give me a negative. And then I can say, well, all right, positive times a negative is a negative. So since my derivative is negative in this region, I know my function is decreasing in that region. I move to my next region. 0 is the test point to represent all numbers between negative 2 and 2. When I plug a 0 into this factored first derivative, I can easily see it's going to be a positive times a positive, which we know gives us a positive first derivative. Thus, our original function is increasing there. Now, between 2 and infinity, I plugged in a 5. When you do that, your first factor is going to be positive. Your second factor, you would have a negative 7 times 5 squared. That's going to give you a large negative number, plus 28 stays negative. Positive times a negative is a negative. Since my first derivative is negative here, my original function is decreasing. Now, the questions that they asked here, it says, write the critical points in increasing order. So unlike other problems where it wanted you to label the critical points all one right after another, this is wanting you to label them one at a time. So the first critical point in order from low to high was -3. The next one was -2. And please don't forget to scroll down. In fact, I did that the first time, I believe, on this problem, all the way down to the last critical point of 3. And then after you do that, you have to be able to answer whether each critical point is a maximum or minimum. Clearly, since I know my function is increasing to 3 and or -3 and decreasing after, -3 is going to be the location of a maximum. What about -2? Well, it's decreasing before it, it's increasing after it. Then -2 is a minimum. What about 2? Well, it's increasing before it, decreasing after it, thus it's a maximum. So I would say I have maximum at -3 and at -2, sorry, and at +2, and a minimum at -2. You just plug that information in and Achieve would be happy. Now for the next problem, it goes back to just being a cubic function, and we're asked to do the first derivative test. So I said, well, okay, in this one, and I'll bring this up here a little bit more. In this one, I had 1/3 x cubed plus 11/2x squared plus 10x plus 5. Derivative is super easy on this. I just have x squared plus 11x plus 10. And notice that derivative factors just by your trinomial factorization really easily. Factors of 10 that sum to get to 11 are 10 and 1. So this factors to be x plus 10, x plus 1. Now, if I set those factors equal to 0 to find the critical point, then we'll get x is -10 and x is -1. Now, I use those critical points to break up the domain of the original cubic function. So I start at -infinity, go to your lowest critical point, -10. Go from that critical point, -10, to your next one, -1. Then you go from -1 to infinity for your last region. And then you say, well, each of these test regions needs a test point. I just found 3 points that all fit within each of these regions. When I plug -15 into my factored first derivative, I will get -5 times -14. It's a negative times a negative. I know it's going to be a positive answer, and thus I know my function is increasing. When I plug in a -5, the first factor would be positive, the second factor would be negative. Positive times a negative is a negative, which means my function is decreasing in this region. And then lastly, I plugged in a 0 to represent the last region. That would be a positive times a positive. So we know our first derivative is positive and our function increases in this region. So we can say just from looking at this, we know that there has to be a maximum at -10. And then it's going to decrease down to -1 and have a minimum. Then it's going to increase after -1. So you should be able to answer all of your questions based upon that. Notice it says F has a local minimum at -1, and it doesn't want x equals -1. It just wants the -1. And it has a local maximum, and we know that's at x equals -10, but we're just supposed to put the -10 part. And then the intervals of increasing, decreasing, just like I have here on my chart. You can say, well, it's increasing whenever the function is going upward. So it's increasing from -infinity to -10. And please don't forget to put the union in between your two groups. So -infinity to -10, union, -1 to infinity, decreasing between -10 and 1. Now for 15, goes back to being a 4th degree function, but it's really easy one because it's a pretty simplistic one. So we just use the power rule to take the derivative, and we'll get 8x to the 3rd plus 9x squared. We set that equal to 0 to find the critical points. When I set it equal to 0, I said, well, it's best if we factor that left-hand side. So I can factor an x squared out. When I do, 8x plus 9 is left over. Now, using the zero product property, I know that 0 is a critical point, and I know that my other critical point would be when 8x is equal to -9, so x would equal -9/8. Now, before I even do this problem, I already know that, yes, I'll have a maximum or minimum value at -9/8. I will not have a maximum or minimum value at 0. And you might be thinking, how do you know you won't? Well, because it was a double root. Remember what the graph looks like whenever you have a double root at a certain x-intercept. It's going to, so the derivative is going to touch at 0 and go back in the direction it came from. If it approached from above, it touches and goes back up. If it approaches from below, it touches and goes back down, which means the derivative is not going to change sign at 0. That means it can't be a maximum or minimum on the original function. A maximum is when the derivative changes from positive to negative, and a minimum is when the derivative changes from negative to positive. So I can say, I know 0 is not going to be a maximum or the location of a maximum or minimum value. But I still go ahead and put it in my first derivative sign test. I go negative infinity to negative 9 over 8, then negative 9 over 8 to x equals 0. It is still a critical point, and then x equals 0 to infinity. Now, choosing test points within each of these regions, I chose -5 to represent the first region, -1 is inside the second region, and 1 is inside the third. Now, when I plug these test points into my factored first derivative, please notice I was saying the factor x squared that led to the critical point at 0. I said, that's really not going to be a maximum or minimum. Please notice that factor also is not going to contribute to any sign changes on my first derivative test. No matter what I plug in, x squared is always going to be positive here. It's only that second factor that gave me the critical point at -9 over 8 that's going to contribute to sign changes. When you plug a -5 in, you would get -40 plus 9, negative. We know we're going to have a positive times a negative in that region. Our first derivative is always going to be negative, which tells us our function is decreasing. When I plug a -1, I know that I would have -8 plus 9. That second factor is going to be positive. Then both factors are positive, and your first derivative is positive, telling you that your function increases. Now, what about in your next region after 0? Well, it's even more positive. In that portion, you would have 8 times 1 plus 9. You'd have the product of two positive numbers is positive. And then you can say, okay, your graph is going to look something like this. It's going to be decreasing until you get to -9 over 8. It flattens out at -9 over 8. And then it increases from -9 over 8 to 0. Remember, any critical point, the derivative is 0, which tells you your original curve flattens off at that point. So it flattens at 0. And then from 0 to infinity, it's increasing again. I'm going to have what's called an inflection point at 0. It's neither a maximum nor a minimum. Please do not say it's increasing at 0. If they ask you intervals of increasing, you would have to say it's increasing from -9 over 8 to 0, union 0 to infinity. It is not increasing at the instant when x is 0. Now, if I look at this question and all the things, notice they go back to having you list all critical points all right there. And then it says on the interval from -infinity to C1, that just means your lowest critical point. So on the interval from -infinity to your lowest critical point, which mine was -9 over 8, I knew that my function was decreasing. And so I put that in there. Then it said on C1 to C2. So from your first critical point to your second critical point, that's this interval right here, it's increasing. That's what I had to put. And then from the second critical point to infinity, it was increasing again. Now for the next problem here, it's going up, still just a polynomial function, but much higher power. 5x to the 7th plus 5x to the 5th plus 5x. Whenever I was thinking about how to work this problem, of course, we had to take the derivative. But then as soon as I took that derivative, I knew I didn't have to go any further. And I want you to know the same thing. You're like, how am I supposed to know that? Here's how you're supposed to know that. Remember, the critical points are going to be values at which the derivative is equal to 0. Please think about this. Can you take any even function like x to the 6th, add another even function, and then add 5 to it and possibly get a 0? You should automatically be thinking, no, because the lowest this could be is at x equals 0 itself, and then this would just be 0 plus 5. If x is any number other than 0, these values are just going up, not down. You would have 35 times a positive number plus 25 times a positive number plus a positive. So I am 100% certain the derivative can never equal 0. All it means is it doesn't have any critical points. So this means that the original function is what's called a monotonic function. It never changes direction. It never flattens out. And I can also see, since my derivative is always positive, then that means that the original function is always increasing. So from left to right, this function is always, always, always moving upward. And so now, whenever you're trying to answer the questions in this one, it just says, well, what are your critical points? D and E. There are none. When is it increasing? Always, from negative infinity to infinity. And then for the rest of them, it's never decreasing. There are no minimum. There are no maximum values. So D and E for all of those. A lot of D and E's are the examples on that problem. Now, for the next one here, it gives me x to the fourth minus 3x to the 3 over 2 power. Now, they really didn't have to tell us that x is greater than 0. Actually, I guess they did. We would have understood that it was implied that x has to be greater than or equal to 0, because this is the square root of x cubed there. And you know that you can't have a negative number inside of a square root, but this is even making it further restricted. It must be a positive number for x. So I'll say, okay, with that in mind, when I'm trying to think about how I worked this problem, I have my function here. I take its derivative. Pretty easy in this case, 4x to the third power. And then I'll have minus 9 over 2 x to the 1/2 power. I went ahead and thought, okay, I know I'm going to need to set this equal to 0. So in an effort to do that, I'm going to, factor it. The way I chose to factor it is I decided I would take a factor of 1/2 out of the constants. You wouldn't need to do that. I chose to do that. And you always factor out the lower power of the variable. That's x to the 1/2. So I factored out a 1/2 x to the 1/2. When I did that, if you factor a 1/2 out of 4, it leaves you with an 8. And then when you factor an x to the 1/2 out of x cubed is the same thing as the 6 over 2 power. So when you're factoring this out, you'll have 6 over 2 minus 1 over 2. You still have 8x to the 5 over 2 for that first term. Now the second term, the x to the 1/2, just cancels that one out. 9 over 2 divided by 1 over 2 leaves me a minus 9. Now I set each of my factors equal to 0. I understand that this first factor, it would only equal 0 if x equaled 0. You'd have 1/2 the square root of x equals 0, you get x equals 0. But we know x cannot equal 0 due to the domain restriction. So I just said, okay, that's not a possibility. So the second factor could equal 0. And I said, well, all right, the second factor would equal 0 if 8x to the 5 over 2 was equal to positive 9. And then that tells me that x to the 5 over 2 would equal 9 over 8. And then the way that you solve this out, the way you have to get rid of the 5 over 2 power. So all I've done from this step to this step is I said, let's raise both sides of this equation to the 2/5 power. X to the 5 over 2 raised to the 2/5 is x. And your right-hand side is 9 over 8 to the 2/5. Now, Achieve is wanting this to be an exact answer, so there's really no need to go to your calculator to see what that's equal to. I'll just leave it as that. I know it's a number slightly greater than 1, and I'll go on over here into my interval test, or I should say first derivative test, first derivative interval test. The domain of this problem started at 0, so I'll start my first interval at 0. I go 0 up to my critical point, and then from that critical point off to infinity. A number between 0 and the critical point, 1 would represent that. Could have also chosen 1/2 or any other number inside that, but 1 works fine. And then a number between your critical point and infinity, I chose 2. Now I'm plugging those test points into the factored version of my first derivative. Clearly, the square root of 1 and the square root, both positive. It's that second factor that's going to change signs. When I plug a 1 into it, I would get 8 minus 9. That's a negative. I'll have a positive times a negative. That's a negative. Tells me my function is decreasing in that region. Now, what about the second portion when I plug in the 2? You would have 8 times the square root of 2 to the 5th power. That's going to be 8 times 4 on the root of 2, certainly going to make that number larger than 9. So this factor would be positive, and you would have a positive factor times a positive factor, yielding you a positive first derivative in that region. So you could say your function is increasing. So we say we have a minimum at the critical point of 9 over 8 to the 2/5. It's decreasing before that critical point and increasing after. So you see, it's asking for the critical point that corresponds to a minimum. That was my answer. There was no critical point that corresponded to a maximum value. So that was D and E. And then you have to state where the function is increasing and decreasing, and it wants it in that exact notation. So you have to be a little careful in how you enter it in. Up next here, for number 18, same type of question, except now for the first time, I'm given a quotient. So I can say, well, all right, no problem. Now, what I would have been checking on this problem is automatically, whenever you have a rational function, you should be thinking, there's restricted values in the denominator. Not in this case, because x squared plus 4 is guaranteed to be positive. So I don't have to worry about restricting values of x that cause the denominator to be 0. So I just head straight forward into finding the derivative. And I said low d high, since the high is a constant function, that whole first product is 0. Derivative of any constant is 0. Then I would say minus the numerator times the derivative of the denominator. And for that, I got my minus a negative 2 times 2x. That just gives me a positive 4x for the entire numerator of my quotient rule, all, of course, over the denominator squared. That denominator becomes irrelevant because the only way that derivative can equal 0 is if the numerator equals 0. Well, the numerator can only equal 0 if x is 0. So our only critical point on this function is that x equals 0. So I take the domain, which again, remember, it's from negative infinity to infinity. I break that up with the only critical point of 0 and go negative infinity to 0 and then 0 to infinity. I chose test points of negative 1 and 1. They certainly fit within each region. When I plugged in the negative 1, and I used this for the version of the first derivative I'm trying to think about, I can say, well, if I plug a negative 1 into the numerator, clearly I get a negative. When I plug a negative 1 into the denominator, I'm going to get a positive. It would be 5 squared. So I have a negative over a positive. My fraction is going to be negative. My derivative is going to be negative, which tells me my function is decreasing from negative infinity to 0. Then on the other side of 0, when I plug in the 1, clearly I'll have a positive numerator and a positive denominator. It would be 4 over 25. I don't care about the specific number. I only care that it's positive. That tells me that my function is increasing on that region. So I can see that the only critical point is 0, and that critical point is going to be a minimum. It's going to decrease before it and increase after it. And you can see it was just asking that C, the critical point 0, and that it is a minimum in this problem. When I look at 18, it continues the trend of number 17, where it brought in a root function. Again, we have the 9 over 2 power. This is understood to be the square root of x to the 9th power minus 2x squared. Again, they're restricting the domain for us to values of x that are positive. Okay, so now when I try to find my critical points, I take the derivative. Power rule on both terms, 9 over 2 x to the 7 over 2 minus 4x to the first. Just like number 17, I said, well, it's easier if I factor this. I need to factor this expression. Clearly, the smaller power of x is the x to the first. And I also, again, factored out the factor of 1/2. So I said I will factor out a 1/2 x. When I did that, that left me with a factor of 9 for the constant in the first term. Then I would have x to the 7/2 minus x to the 2/2 gave me x to the 5/2. My second term, 1/2 divides into 4, leaves me an 8. So I have minus 8, and then of course the x canceled out. Now, the first factor, if you use the zero product property and set it equal to 0, you would get, hey, x is 0. But it can't be in this problem. It's not part of the domain. So the only critical point I'll get is from my second factor. And in that second factor, you would say, well, then 9x to the 5/2 must equal 8. So x to the 5/2 must equal 8 divided by 9. And then similar to 17, I raised both sides to the 2/5 power. This time I'll get 8/9 to the 2/5. Now, unlike 17, where it wanted me to keep the answer in exact format, it didn't want that this time. So I went ahead, went to my calculator and said, let's take 8/9 raised to the 2/5 power, and I got 0.954. So now we're saying our first test interval is from 0 up to this critical point, and then we go from the critical point to infinity. I chose test points within each region. 1/2 fits nicely in the first one, and 2 certainly fits in the second one. Now, we're plugging that 1/2 and that 2 into your factored form of the first derivative. You plug in either of these x values, your factor 1/2 x stays positive no matter what. But now when you plug the 0.5 into the second one, you would have 9 times 0.5 to the 5/2 power. That's going to be 9 times a very small decimal minus 8, makes that factor negative. Now I'll have a positive times a negative. My first derivative is negative there, which means my function y is decreasing from 0 to that first critical point. Then when I plug in a 2, you'll have 9 times the square root of 2 to the 5th. That's 9 times 4 on the root of 2. And you can say, well, that number is certainly going to exceed the size of 8. So you have a positive for that second factor. 2 positives make a positive product, and we can say our first derivative is positive in that region, which tells you your function is increasing. So then, again, Achieve will want the decimal answer, not the 8/9 to the 2/5. That's your critical point, and we can see that that critical point is a minimum on this one. It's decreasing before, and it's increasing after. Now, the next one here, and the last page of the work I did for this section, it took me 6 pages to do the Achieve assignments in this section. For number 20, I have 5e to the negative x cosine of x, and it's restricting me to the interval -pi/2 to pi/2. So of course, I have to take my derivative, and this one, like very few of the other ones in this section, we need to use the quotient, sorry, not the quotient rule, the product rule. So I said, well, derivative of the first, that's going to be 5e to the negative x times -1. That's where I got the -5e to the negative x. All of that's the derivative of the first times the second, plus the first, now times the derivative of the second. Derivative of cosine is negative sine. So now here's my first derivative. I need to factor it so I can set it equal to 0. Quickly and easily, I said, well, I could factor out a factor of -5e to the negative x out of both terms. I did that. When I did that, I saw that I would be left with cosine x plus sine of x for my remaining factor. I set this equal to 0. That first factor, it can't equal 0. And if you rewrite e to the x with a positive exponent, it makes it very clear. That's the same thing as -5 divided by e to the x. I can't divide -5 by e to the x and ever get a value of 0. It's always going to be something other than 0. Now, it asymptotically approaches the x-axis, but it's never going to equal 0. Now, for the second factor, no problem at all. When is cosine plus sine going to equal 0? Well, when cosine is the negative of sine. And the cosine is the negative of sine. Now, if you just think in terms of the normal unit circle, you could say, well, they're opposite values at 3 pi over 4 and 7 pi over 4, because at 3 pi over 4, we have the cosine negative square root of 2 over 2 and the sine the positive square root of 2 over 2. And at 7 pi over 4, it's the reverse. The cosine's the positive square root of 2 over 2 and the sine's the negative square root of 2 over 2. But I had to be careful because we're just from negative pi over 2 to pi over 2. So coterminal angle to 7 pi over 4 is your angle, of course, negative pi over 4. That's my only critical point within this region of interest. So then I say, okay, when I do my first derivative sign test, where this function begins, negative pi over 2, up to my critical point within, negative pi over 4, then from that critical point to the end point of my region of interest. I choose a test point in that first region. Negative pi over 3 fits nicely between negative pi over 2 and negative pi over 4. And 0 certainly fits nicely between negative pi over 4 and pi over 2. I plug that into my function. This first exponential function, negative 5 over e to the x, no matter what you plug into that, you're always going to get a negative. So I just went ahead and showed that. Now, it's this second factor that's going to matter. When I plug in a negative pi over 3, now you need to be thinking in terms of the unit circle. Negative pi over 3, same thing as 5 pi over 3 on your first rotation of the unit circle. Your cosine's the negative square root of 3 over 2. Your cosine is positive 1/2. The sine is negative square root of 3 over 2. It goes down more than it moves to the right. And so you'd say, well, in this first region, then you'd say, well, the cosine is 1/2. Your sine is the negative square root of 3 over 2. 1/2 plus a negative square root of 3 over 2 is going to be a negative. So I'd have the product of two negatives. That's a positive. And I know my function is increasing initially up to that critical point. What happens after the critical point, though? I plug in a 0 to find out. Clearly, my first factor is still going to be negative. It'd be a negative 5 divided by 1 because e to the 0 power is 1. And my second factor, it would be positive because we know the cosine of 0 is 1, sine of 0 is 0. So that's just 1 plus 0. A negative times a positive is a negative. We can say our function is decreasing in that region. Now, for the last two here, similar types of problems. For number 21, while it's a similar problem, it's more beautiful because it brings in an inverse trig function. But remember, you just have to have those inverse trig derivative formulas memorized. As soon as you see inverse tangent of x, you should be thinking its derivative is 1 over 1 plus x squared. Boom. Now, this had a 6 out in front of it, so it's 6 times 1 over 1 plus x squared. I just went ahead and put the 6 in the numerator. Derivative of minus 3x becomes minus 3, and I set this first derivative equal to 0. Now, in order to find the critical points, I'll move the 3 on over to the right-hand side, and then I'll multiply both sides by 1 plus x squared. That's going to give me a 3 plus 3x squared on the right. I move that 3 to the left-hand side. 6 minus 3 is 3. So now this really simplifies nicely. I'll divide by 3 on each side, and I get x squared as 1. Now, please, please, please remember that x is both the positive and negative square root of 1. I can see a lot of people making a careless mistake and thinking x is just 1 there. I have both of these are critical points. I plug those critical points into the domain of this problem, which the domain of any inverse tangent function is always negative infinity to infinity. So I go negative infinity to my lower critical point at negative 1. Then I go from that lower critical point to the higher critical point, negative 1 to 1, and then 1 to infinity. We plug in test points that are inside each of these regions, and then think about what that's going to do. Now, I didn't have a factored first derivative like I normally do, but you can still plug it in. And in fact, you'll see I plugged in the actual numbers here. When I plug in a negative 5 into this expression, I would get 6 over 1 plus 25. That gave me 6 over 26. I'd be subtracting a 3 from that. Clearly, that's a negative number. My function's decreasing in that region. When I plug in a 0, I would have 6 over 1 minus 3. That would be a positive. Function's increasing in that region. Now, what about the last region? Well, it's going to be the same as the first. Whether you plug in a 5 or a -5, this first portion is going to be 6 over 26. You're subtracting a 3 from that, and that's showing you that your first derivative is negative in that region and that your original function must be decreasing. From this, it just wanted you to determine the minimum and maximum value. I'll have a minimum at -1 since it's decreasing down to that point. Then it's going to be increasing up until it gets to 1. It'll obtain a maximum and then start decreasing after that. Now, the last problem here, it was a bit of a fun one. So it gave me something, well, it didn't give me something that looked like it. It did look exactly like this. I had a function of x as the coefficient of an exponential function e to the x plus 11. Just to make sure you see it here. That's how it looked on my screen. And now, the thing about this one that makes it interesting is it's wanting exact answers. And that became a little tedious in this problem. So let's talk about that. It's certainly the hardest and most beautiful problem in the section. So I thought, well, all right, this is my original function. In order to determine when it has any critical points, when it's increasing or decreasing, I have to take the first derivative and set it equal to 0. Clearly, the derivative of 11 is 0, so don't have to worry about that. It's just this first term. In that first term, it's a product. So I said, well, all right, I'll have to use the product rule. Take the derivative of the first portion of that term. That's where I got the 3x squared minus 486 over 5 times the second, plus the first, all of that group, times the derivative of the second, but derivative of an exponential function is still that exponential function. So then I said, well, all right, I have all of this. It's my first derivative. I need to try to simplify that out. And in the simplification, I just said, well, clearly I could factor an e to the x out of all terms. And when I do, I'll have an x cubed plus 3x squared minus 486 over 5x, and then minus 486 over 5. Now, I need to set this equal to 0 to find my critical points. Now, clearly, that first factor cannot be 0. E to the x, it only asymptotically approaches the x-axis, so I don't worry about that. But I was thinking, okay, but now we're tasked with trying to set this cubic equal to 0, and that cubic certainly does not factor nicely. So here's what I did. I'll go ahead and show you here graphically. I went in here and I took my function, the x raised to the third plus, oops, let me make sure I get out of the exponent, yeah, plus the 3x to the second minus 486 over 5x, and then minus 486 over 5. Now, I made the assumption that it most likely has some x-intercepts between -10 and 10. So I just graphed this on the standard Zoom screen. I said Zoom 6. Now remember, I don't care how good of a graph this is. I only care if it shows me where it's crossing the x-axis. That's going to let me know what the factors are and what the zeros are. So I have a y2 set equal to 0. I think that's a nice thing too, because then on my graph, I can go into second calculate. I can find an intersection of where my first curve intersects y equals 0 with my second curve. So I just go second count 5, enter, enter, enter. And it's telling me, okay, you have an x-intercept at -0.9800398. Not helpful. That's an irrational x-intercept. I don't care about that. So I try again. I'll say, well, it's got another one over here. I'll try to find that one. Second count 5, enter, enter. You could scroll over, or it looks like my guess. Well, in fact, I'll just scroll over. It doesn't take long. As long as your cursor is closer to the other point, you'll be fine. You have to hit enter. And when it says intersection, this is showing, okay, he has an x-intercept at 9. Now, I know that x equals 9 is a root. So then I can say, well, then I should be able to synthetically divide 9 into all of these coefficients, and it's going to enable me to reduce this down to a quadratic. That's what I do. So using synthetic division, I bring the 1 down. 9 times 1 is 9. I sum the next column. 3 plus 9 is 12. Then I had 9 times 12 is 108. I used my calculator to add the next column and simplified it to a fraction, 54 over 5. 9 times 54 is going to give me, or not 9 times 54 over 5 is going to give me my 486 over 5, which gorgeously cancels out that last term. And of course, we already knew it had to cancel out. You had to have a remainder of 0. Now, what this tells me is that the cubic part of this, that's the only part that's going to have any critical points, would factor to have a factor of x minus 9. That's because it has that root. And the other factor is going to be x squared plus 12x plus 54 over 5. Now, I wasn't thinking, well, okay, great, I can factor that. No, I can't factor it when that c term is a fraction like 54 over 5. So as soon as I got to this, I kind of just said, well, let's take the chicken way out now, and I'll use the quadratic formula for the remaining 2 factors. And I know they're irrational anyway. I saw that one was like negative 0.9803 something. So using the quadratic formula for the remaining factors, I just say x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, and plugged in my a, b, and c into that. Then it just became a calculator exercise. I took the 144 minus 4 times 54 over 5. I got the square root of 504 over 5, which I later just called the square root of 100.8, same thing. And so I know, and just to kind of get an idea of where these are at, now Achieve does not want a decimal approximation, but I went ahead and did negative 12 minus the square root over 2, and I got approximately negative 11.02, and then I did negative 12 plus the square root of 100.8 all over 2, and I got approximately the negative 0.98. So that just enabled me to see where these align up with my 9. Clearly, the most negative critical point is the negative 12 minus this square root. So you'll see I broke up my interval from negative infinity to the lowest critical point, the negative 12 minus the square root of 100.8 over 2. Then I went from that critical point to the next critical point, which is still going to be a number less than 9. So negative 12 minus the root of 100.8 over 2 up to negative 12 plus the square root of 100.8 over 2. And then I go from that critical point up to my last critical point, which is 9. And then I go from 9 to infinity. Now, I know I have all 3 critical points accounted for in my test interval, in my 4 test regions for that test interval. Now I choose test points. A number between negative infinity and negative 11.02, I chose negative 20. A number between negative 11.02 and negative 0.98, I chose negative 5. A number between negative 0.98 and 9, I chose a positive 5. And then a number between 9 and infinity, I chose 10. Now, I'm plugging in all of this into the factored version of my first derivative. I had the e to the x, I had x minus 9, then times all of this quadratic factor that would not further factor nicely. So then I can say, all right, if you plug a negative 20 into that. Now, also, let me just go ahead and mention that exponential function, notice, it didn't lead to any critical point. It also does not lead to any sign changes. No matter what you plug in, it's positive. What about that second factor, x minus 9? Well, I'll go ahead and evaluate it at each of the values. When you evaluate it at negative 20, it's a negative 29. When you evaluate it at negative 5, it'd be a negative 14. When you evaluate it at 5, it's still a negative, it'd be a negative 4. When you evaluate it at 10, it'd be finally positive, it'd be a positive 1. Now that last factor for that quadratic, Anytime the power on the x is going to be a large number, whether negative or positive, it's going to be a positive because that x squared, negative 20 squared, that's going to be a positive 400 in there. And so I can say when I plugged it in to the first one, it was positive. When I use a negative 5 in there, all of this gave me a negative value. When I plugged in a 5, it gave me a positive value because of that middle term being plus 60 as opposed to up here where it was negative 60. And then when I plug in a 10, of course, it's going to be a positive again. So now, when I plugged in a negative 20, I saw that there was only one negative factor in my product for the first derivative. Thus, my first derivative is negative, and the original function is decreasing in that region. When I plugged in a negative 5, I had two negative factors, which means your first derivative is positive, and the original function is increasing in that region. When I plugged in 5, I only had one negative, which means your original function is decreasing since your first derivative is negative. And the last region, every single factor of the first derivative was positive. So our first derivative was positive and it's increasing. Now, it's going to ask the maximum and minimum values. Clearly, it decreased to this first critical point and increased after. So I would have a minimum at negative 12 minus the square root of 100.8 over 2. And then it's going to increase up to this critical point and decrease after. So I would have a maximum at negative 12 plus the square root of 108 all over 2. And then what about at 9? Well, it's decreasing before 9, increasing after 9. So I would have another minimum value at 9 since it decreased before and increased after. And that would be all the extreme values of this cool looking function for 22. Now, it's also going to ask values where it's increasing and decreasing, but you can just pull that in based upon where you see it's increasing, decreasing on your chart. So it's decreasing this region, union, the third region. It's increasing the second region, union, the third region. And please do keep in mind, you've got to be very precise keeping the values you got from your quadratic formula. It doesn't want decimal approximations. Okay, guys, I will stop with this. Please let me know if you have any questions. This is a pretty cool section.